Hi there, myself Madhav Jha. I welcome you to CodeChef and let's have a look at this question.
The problem is leave no witnesses. The problem difficulty is easy and you need to know about bit masking to solve this problem. Let's have a read at the problem. We have a string b and its binary of length n. Now what we are going to do is we are going to consider an integer x and x will be a witness if it can follow the following conditions. Now since b is a binary string, its element will be 0 or 1. So if the element is 0, what we are going to do is we'll have a AND bucket and we're going to store x and bitwise AND with I index here. In case we have a one element, what we're going to do is we have this another OR bucket. We'll store the bitwise OR of x and I. We are going to do this for all the index values of I. Now, this makes our set S1 and our set S2. Now, if at the end, once we have traversed over all the indices, if there are no common elements between S1 and S2, we'll say that X is a witness of B. Here is an example that we can follow, but let's move ahead and let's see what we actually have to do. Now, we are given a binary string A of length n, and now our task is to make sure that we can choose some indices in this and we can flip it. So if it's 0, we can make it 1. If it's 1, we can make it 0. We'll have to find the minimum number of operations, and what we want to do is we want to convert this binary string in such a way that there is no witness for this array among the integers 1 to n, and if this is impossible we can simply print -1. Let's see the input format. So we have t test cases, and for each test case we will have two lines. The first line will contain the integer n, that is length of our binary string, and on the next line we'll have the binary string itself. As for the output, we simply have to output the minimum number of changes that we will do in such a way that going from the numbers 1 to n, there is no witness, and in case if it is impossible, we'll simply print -1. As for the constraints, number of test cases will go from 1 to 10 raised to 5, and value of n will go from 1 to 2 into 10 raised to 5. Since what we have is a binary string, it can only contain the characters 0 and 1. Let's see how we can approach the solution. So we know that in the given case, we want to have no witnesses. If there are no witnesses, it would mean that there is common element in our AND bucket, in our OR bucket. So with 0, we can create a AND bucket, and with 1, we create a OR bucket. So for them to have same elements, what would it mean? It would mean that x AND of I is equal to somewhere x OR of j. Now this essentially means that if you are doing an and the elements are same, what does that mean? So if we have x going AND with I, this has to be equal to x, right? Why? Because when we do a AND, the result is always going to be less than equal to x. And if you do any kind of OR, the value will always be greater than equal to x. So the only common point that we have is that both of them are x. Now in this case, what we are saying is that x and with I, we want to be have to be equal to x, and we want the other index j to be equal to bitwise OR, and then still to be the same. So now for in this case, if you are doing this, remember x can go from 1 to n, and so goes for the I. So let's say we have set our x for one particular x, let's say we are checking. So in which case this our x is going to be equal to x when we do an OR. It would mean that all the bits that are present in x are also present in I. That would mean that x, this I has to be a super mask of x. In short, I has all the set bits that are present in x. So let's take an example. If I have 7 with me, 7 looks something like this. Now any I that I have, right? Let's say this is our I because we want I to be a super mask, right? Now any x that has something like this, we have 3, we have 5, we have, sorry, and we have here 1. Now in this case, if you observe, for all these 3 x's, this is a super mask, and if you do a bitwise AND, you will get x back. What goes about OR? Now, if I want OR to be the case, What I would want for J is J has to be a submask, the opposite of this. In this case, our I was the superior that had all the set bits. In this case, X will be the superior and I has to be the submask. Only then we'll get X back. So for this, let's see how we can find it. So what is the best submask that we can get? That will be 1. Why? Because 1 will only have a single set bit. Now, if you do OR with any odd number, it will give you X. That's very good for us, right? We have solved the submask issue. Similarly, what about even numbers? So for even numbers, all the other bits could be set, but this will always be 0. The first bit will always going to be 0 and rest of them can be 1. So for this also, we would want if we could have a single bit with which we'll do OR and can get our X. So what we can do is, let's do the power of 2. So if we have a power of 2, let's see how it looks like. This is 2 raised to 0, this is 2 raised to 1, and this is 2 raised to 2. This is 1, 2, and 4. So now with this, if you perform any OR, there is only one bit involved. So we have a high probability that this is a submask. What about this supermask? So if you want to find supermask, what we can do is we can start looking from the last elements and check what element do we have that will be a good supermask for some of the values of our X. So for this, what do we need to do? So this means that for the elements that are power of 2, that is for those indices that are power of 2, we want to make it to have go in the OR bucket. Why? Because if this goes into AND bucket, only these bits will survive. All the others will be 0. So what we want is all the 2 powered bits to go in the OR bucket. So our OR bucket is now set. And to have the other elements that are in AND bucket, we need to make it 0. So it means that we are going to find our supermasks. So for that, we can start from the end and go till 1. Any number that we find here as n, we will assign it to be a supermask if the number that we are checking, we do a AND with and we get the same number, then that number is going to be a supermask. And for it to be a supermask, it has to go into the AND bucket. So we need to make sure that the index that we have has a 0 in it. It is 0, right? So we'll make the element at that index to be a 0 for our supermask. Then we'll move ahead and check the other numbers. We'll check the other numbers if they with this, if they are not a supermask, then we will have to set it as a supermask and we'll set it to 0 again. So what we are doing is for all the indices that are power of 2, we'll set it to 1 and then we'll search for our supermask. If we find it, we'll make sure that it is set to 0. Once we are done with this, what we'll have is for any number in the X bucket, we'll have a supermask that will put it in the AND bucket also. So there will be a common element. And since we'll have a common element for all the values of X going from 1 to n, we'll make sure that none of the X are witness. And with this, we'll have our solution. Let's see how we can implement the solution in C++. So for each test case, we call the function solve. In solve, we take the input of n, then we have our string s. Since the indices go from 1 to n, we add an additional 0 here so that we can follow the normal index. Then we have a special case here. That is, what would happen if our n itself is a power of 2? Well, in that case, since we are making our power of 2 indexes to go in the OR bucket, we'll need to find a supermask. But there is no element greater than n, so there will be no supermask. So this is the only case where it will be impossible to have no witnesses. Therefore, the answer would be -1. Next up, we go and change all the indices that are power of 2. If the element there is not a 0, we increment it and we change it to 0. Next up, we start going to find our supermask. We start with the end. So supermask in AND with I, if it is giving us I, it would mean that it is fulfilling the condition of being a supermask. So in that case, we simply continue. If that is not the case, what we are going to do is we are going to change the element at that index so that this becomes one of the supermasks and we can put the result in our AND bucket. So with this, we will have a count of all the elements that we need to change such that there are no witnesses. It would mean that There are common elements in our AND bucket, in our OR bucket. And as you can see, I've got an EC in my C++ implementation. Let's see how we can implement this in Python. Again, for each test case, we call the function solve. In solve, we take the input of n and then s. If our n is a power of 2, we return -1. Next up, for all the indices that are power of 2, we change it to 1, and if we change it to 1 and keep a count of the elements that we have changed. Next up, we start to find a supermask. Once we have a supermask, we check all the elements that fall under it. Anyone that doesn't fall, we change it, and we keep a count of the indices that we have flipped. At the end, we print this count, and as you can see, I've got an EC in my Python implementation as well. So I hope you understood the problem, the approach, and how we can implement the solution in both C++ and Python. Have a very good day, and I'll see you in the next video.